Now, Vsepr, or valence shell electron pair repulsion theory, is basically a theory that tells you about the shape of a molecule. Now, the thing is that you might have been drawing Lewis structures on like a 2D diagram. However, it's important to point out that molecules, well, they exist in 3 dimensions. So what's going to happen is that if you have an atom, right? Let's just say if I have atom A, right? And let's say if it's bonded to two other atoms, right? Let's say it's bonded to other atoms, atom B. And let's say if atom A has a lone pair of electrons. Well, what valence shell electron pair repulsion theory, or Vsepr, tells us is that, well, these atoms and these sort of lone pairs, they're going to be trying to get as far away from each other as possible in 3 dimensional space. And the reason why is because, well, remember that, well, whatever bonds you have, they're going to be made up of electrons, right? And lone pairs, well, they're just lone pair like electrons, right? So, of course, when you have a negative charge, right, because electrons are negative charge, you have a negative charge and you have a negative charge. And like charges, they repel each other. So Vsepr takes into account the fact that, electrons, these type of bonds, right, they're going to try to repel each other, and that's going to affect the shape of the molecule. All right. Now, the shape of a molecule is super important. It's going to affect its polarity, and therefore the polarity affects how it reacts with other sort of different compounds. It's going to affect physical properties, right? Remember intermolecular forces, right? The stronger the intermolecular forces, the higher the boiling point, or that's going to affect solubility, like like dissolves like, things like that. There's a reason why when you're drawing water, H2O, there's a reason why you don't draw it like this. All right. There's a reason why water is actually polar, not nonpolar. If you draw it like this is assuming that water is nonpolar, right? This is a diagram that shows that water is nonpolar, even though that's not the case. Water is polar. If water was nonpolar, that would be pretty bad. If water was nonpolar, there would be no hydrogen bonding. So that would make the physical properties of water very different, right? Water would be easier to boil, right? Water wouldn't dissolve as many substances, polar substances. Water's called the universal solvent, so it's able to dissolve a lot of things, right? Like salt, for example, right? If water was nonpolar, it would not be able to dissolve salt because when you're dealing with polar things, right, they're going to have the partial positives, partial negatives, blah blah blah. But I'm just saying all of this just so that y'all get the sense that this is like a very important thing, of the shape of a molecule and everything. So to understand shapes of molecules, let's start off by explaining what steric number is. So steric number just represents is equal to the amount of atoms bonded to your central atom plus the amount of lone pairs on the central atom. So for example, if I have a molecule that looks something like this, right? What is this molecule's steric number? Well, how many atoms are bonded to my central atom? Well, there's 2 atoms, right? 1, 2. And how many lone pairs are there? Well, there's 1. So 2 plus 1 is equal to 3. This corresponds to a steric number of 3. All that represents is that there are 3 regions of sort of electron density that we're going to be focusing on because, well, the electrons repel each other. So that is what we are going to be focusing on. Let's take a look at an atom with a steric number of 2. All right. And so basically, down here tells us the steric number, and then over here tells us how many lone pairs is that molecule going to have. So when we have a steric number of 2, we're just going to be focusing on 0 lone pairs, because think about it, right? Imagine if we have just a molecule where there's a lone pair, let's say here, and then there's 1 bond. So notice how the steric number, remember, it's the amount of atoms bonded to a central atom plus the number of lone pairs on the central atom. So if I say this is the central atom, right, there's going to be 1 bond, right? So it's going to be 1, and there's just going to be the lone pair, so 1 lone pair. That gives me a steric number of 2. This is just going to be a sort of straight line structure, right? Because you're only bonded to 1 atom. So at the end of the day, this is just going to be a linear sort of structure, right? So yeah. Anyways, now that we got that out of the way, we can start looking at the structures. So when your steric number is 2 and you have 0 lone pairs, well, you're going to have a linear structure. All right, so you have your central atom, and it's going to be bonded to 2 atoms at the side, and they're going to be trying to get as far away from each other as possible. So this is going to be the optimal sort of structure. It's going to have a 180 degree. It's going to have a 180-degree bond angle. Okay. Now, a lot of times, VSEPR theory is very hard to visualize. So for that reason, I actually have a simulation here. This is the FET Colorado. Very good. You guys should check this out. I'll have it in the description. Essentially, look, this is my central atom. Let's say if I add 2 bonds to it, this is going to be a linear structure. It's going to have a linear structure. The bond angle is going to be 180 degrees. Okay? Now we're going to be focusing on a steric number of 3. Let's say if we have an atom, a molecule where our central atom is bonded to 3 things, 3 other atoms. This structure is called trigonal planar, and this is going to have 120-degree bond angles. 120-degree bond angles. You can see how it kind of looks like a little triangle, right? So if I go back to my simulation and I add another bond, well, now we have a trigonal planar structure. All right, now we have a trigonal planar structure. So this is what it is going to look like. And down here we have electron geometry and molecule geometry. So I'll explain kind of what those are a little bit later. So actually, I'll explain it really quickly here. So after a trigonal planar, right? Imagine if we took a trigonal planar structure, and imagine if we made, instead of one of these atoms right over here, what if this was a lone pair, right? So imagine if we took the trigonal planar structure and we made essentially one of the bonds, we turned that into a lone pair. Our steric number is still going to be 3, but now we're going to have 1 lone pair. And what's going to happen here? Well, notice how this structure kind of resembles a trigonal planar structure, right? So if I get rid of one of this and I add a lone pair, right? Notice how even though we remove the bond, it still resembles a sort of trigonal planar structure. So that's going to be our electron geometry, right? It's going to be sort of the geometry if we kind of pretend like the electron is like a sort of bond, right? But in reality, if we were to only look at the molecules, if we were to ignore these lone pairs and only look at the shape of this molecule right over here, it's going to be a sort of bent structure. It's going to be a bent structure. Okay, so right over here, I started to share my screen. All right, so look, imagine if we assumed that these electrons were a bond. Imagine if this was a bond. Well, we would have a trigonal planar structure. But the actual structure of the molecule, this is going to be a bent structure. What's going to happen is that these electrons are actually going to push, they're going to repel the sort of electrons in this bond right over here. So the electrons that these atoms are sharing, the electrons are going to repel this sort of bond, right? And that's going to make this bond angle less than 120 degrees, right? You saw with trigonal planar, you have this bond right over here, and this creates a 120-degree angle. However, the thing to know about Vsepr theory is that, well, lone pair electrons are going to push more, they're going to sort of repel more on the other atoms bonds, right? On the other bonds found in the molecule. And that's going to make their bond angle less than what you would expect. Okay? Now let's look at an atom with a steric number of 4. All right, so what I want, kind of the theme of this, right, is I'm going to look at sort of a molecule where there's no lone pairs, and I'm going to pretend like you add a lone pair, right? Imagine if this was a lone pair. Imagine if this was a lone pair, right? I just keep on adding more and more lone pairs and see how the shape sort of changes. Let's say if we have a tetrahedral structure. This is where things start to get complicated, and we start getting an introduction into a sort of 3 dimensions, all right? This is where the 3-dimension stuff starts popping out, all right? So in this case, you're going to have sort of wedges and you're going to have sort of dashed lines. Wedges represent the fact that this atom is sort of poking through the screen. Like you can imagine this atom sort of coming towards you through the screen. And the dashed lines represent that this atom is going backwards towards the screen. And if you just have a central atom bonded to 4 other atoms, no lone pairs at all, this is going to be a tetrahedral structure. This is going to be way better if you were to visualize this. All right. So here is the tetrahedral structure. And let me see if I can make it match up with what I have here. So this is the tetrahedral right over here. And let me see if I can make this match up. So it's going to be like this, right? Notice how, right? Actually, it's going to be like a little bit like this. All right. Notice how, right, you have these 2 right over here, right? these two right over here. But then you have this one right over here, this one right over here, and this bond is sort of, you see how it's poking towards you through the screen, right? It's coming towards you through the screen. And then the other bond is going away from you, right? That's what the dashed lines represent. This is a tetrahedral structure. Imagine if we took one of the bonds and we decided to put a lone pair there. So there's still 4 regions of electron density. However, what's going to happen is there's going to be lone pairs here. All right, there's going to be lone pairs there. And what that's going to do, once again, this is going to push on sort of the bonds of the other sort of parts of the molecule, right? So if you were to originally look at a tetrahedral structure, you would find out that the bond angles is 109 degrees, 109.5 if you want to be exact. But, or more specific, I guess, not exact. But for a trigonal pyramidal, sort of a trigonal pyramid sort of structure, the bond angle is going to be less than 109 degrees between the atoms in this structure, okay? The reason why we say it's less than 109, once again, is this valence electron kind of, these lone pair electrons sort of repelling these sort of bonds. It makes it sort of come close together and reduce the angle that it originally was, right? It reduces the angle that it originally was. And if you just wanted to visualize this, here you go, right? Here you go. This is going to be the structure right over here. Imagine if I took away the lone pair, added this, it's going to be tetrahedral. When I add the lone pair, trigonal pyramidal. All right, sort of looks like a pyramid, right? It's sort of like a triangle, and it's like a sort of pyramid. So yeah. Then, if I took this atom right over here, and I turned it into a lone pair, then now notice how I have 2 lone pairs, and this is a bent structure. All right, this is going to be a bent structure. So imagine if I took away another one of this and I added, boom, another lone pair. This is what it's going to look like, okay? And let me see if I can get it in the correct angle to show you guys, to make it, I'm trying to make this into the correct angle. This is like, all right, there we go. There we go. Okay. So look at this bent structure right over here. So it looks like you have 2 atoms, right? This line's right over here, okay? 2 atoms, lines are over here. Okay, that seems normal. All right, those are the 2 lines. But then things start getting weird. Then we introduce the factor of 3 dimensions. This right over here represents that this electron is pointing sort of away from you, right? This is going to be the dotted line, the dashed lines. So notice how you have one of the things away from you. And on the other hand, you have a wedge right over here. This is going to be pointing towards you. And well, that's exactly what we see here, right? This is coming towards your screen, right? So it's like that. All right, we have a bent structure. And the bent structure, this is actually going to be a lot less than, quite a bit less than 109 degrees. I can't give specific angles out because, well, it's different for every sort of bent molecule that I have. But, just know that's going to be a lot less, quite a bit less. Not like a lot, like as in like it's going to be like 3-degree bond angle. But like it's just going to be like a little bit more than, a little bit less than 109 degrees. All right, it's going to be a little bit less. Now we have a steric number of 5. All right, so now imagine if we have a central atom bonded to 5 atoms. All right, so this is going to be a trigonal bipyramid structure. All right, and take a look. I really like trigonal bipyramid because guess what? We have 1, 2, 3, 4, 5. All right, this is going to be the trigonal bipyramid structure. Okay. Now, I want you guys to take a look at this. All right? So I want to arrange it this way, like this. Oh my God, this is like so hard to control. If you guys visit the simulation, you'll find out this is pretty hard to control. Anyways, all right, there we go. All right, so this is a trigonal bipyramid. You have 1 pointing away, and yeah, that makes sense. And you have 1 pointing towards. All right, that makes sense. All right. Notice how, if I just look at it from sort of this angle right over here, notice how it forms like a straight line. And this is like a 90-degree angle, right? So these are 90-degree angles right over here. So let me just write that down. All right. But what about the other angles? Well, look up here. This is where things get interesting. Notice how when I flip this molecule up, sorry guys, notice how when I flip this molecule up, notice how this looks like, whoa, this looks like a trigonal planar structure. That's weird. Look, 90 degrees, but then when you go up, look at it from an upwards perspective, this looks like whoa, this looks like a triangle. And remember, this is a sort of a trigonal planar structure. And remember what angles trigonal planar has? 120-degree bond angles. So these angles right over here are going to be 120 degrees. These angles are going to be 120 degrees, you guys. Okay? So there we go. Right? You can see how the way I like to think about it is this right over here, it forms like a triangle, like so. And then this one forms like a sort of rectangle. That's how I like to see it. Okay? The angle between the top atom and all these other atoms is going to be 90 degrees. So this is going to be 90 degrees. This is going to be 90 degrees. It might be a little hard to see, but imagine, look, this, so this atom right over here, right, it's going to form a 90-degree angle with all of these other atoms, right? You can see it from here. This forms a 90-degree bond with all of the other atoms. You can think about this as this is sort of the y-axis, and then all the other atoms are on the x-axis. So the y-axis is going to form a 90-degree angle with all of them. It's going to form a 90-degree angle with all of them if we're looking at the angles for the top atom. So I'm just going to draw here. It's going to be here. This is going to be 120 degrees. Okay. Now imagine if we took one of these atoms, we turned it into a lone pair. Well, now we are going to get something known as a seesaw structure. Okay? Let's take a look. The reason why it's called a seesaw is imagine if you actually put this structure on like a table. If you actually put this structure over here on a table, it would kind of be like a seesaw. Let me show you guys what I mean. Yeah. Imagine if you put this structure on a table, right? So it's going to be like a seesaw, right? It's going to drop to one side, and then it's going to rotate to the other side, right? Let's see, here, and then it's going to go down here. All right, it's kind of hard doing it with this simulation, but just know that if you kind of place this, imagine placing this on like a table, you can kind of rock it back and forth like a seesaw, right? This atom's up. Imagine if you push it down, then the other part's going to go up. If you push this one down, then the other part's going to go up, right? So it's kind of like a seesaw, if you're actually to do that. Anyways, well, you would expect that, well, knowing Vsepr and, everything I just said, well, you would just kind of assume that, this angle right over here would be now less than 90 degrees, right? Originally, this angle right over here was also 90 degrees, right? But now, knowing that valence electrons, or these lone pair electrons that are not bonded to anything, knowing that they're going to push on the bond angles a little bit more, right? That's going to sort of make these atoms come a little bit closer, and that's going to make this bond angle less than 90 degrees, and that's going to make this bond angle less than 120 degrees. Whenever you see a valence electron, sort of these unbonded electrons, the lone pairs, you should be thinking, oh, less than, and then some degree, okay? All right. Let's say we have two valence electrons now. So now instead of two atoms, we have two valence electrons. All right. Actually, I want you to note something also here. For the seesaw structure, notice how it's not a perfect 180-degree angle. It's actually a little bit bent, if you can actually see that. Right? You see it's a little bit bent, right? If I were to add this, actually, look, this is going to be 180 degrees perfect, right? If I had a lone pair, and I were to look at the linear sort of structure, it would be a little bit less than sort of what it originally was, because these valence electrons are going to be repelling against that. All right. Let's see. We have two lone pairs. All right, we have two lone pairs now. What is this? If we have two lone pairs, this kind of looks like a T shape. That's exactly what it's called. It's called a T shape. All right. Now, the thing about T shapes are that, well, their bond angle, it's going to be less than 90 degrees, right? You see, we've maintained the 90 degrees here, right? This is going to be less than a 90-degree angle. All right. It's going to be less than 90 degrees. All right. Let me see here. All right. Good. And finally, imagine if we have three lone pairs. So imagine if I just took this out. Place a lone pair there. This is going to be a linear structure, okay? So with three lone pairs, but with 5 regions of electron density, this is going to be a linear structure. So this right over here is going to be linear. However, you might expect that this structure is a little bit weird with the bond angles, but nah. This bond angle right over here is actually 180 degrees. All right. No clickbait this time. All right. Nothing weird this time. All right. Now finally, let's move on to atoms with a steric number of 6. Atoms with a steric number of 6. First of all, let's just look at sort of the original atom, right? Or I mean, the original sort of molecule. Sorry guys if I've been saying like atom a lot. But let's take a look at original molecule that has all six bonds, no lone pairs. This is going to be an octahedral. All right, take a look at this. Notice how if you look up top right over here, 90-degree bond angles. Right. If you look at this perspective, if you look at the top perspective, this looks like it has 90-degree bond angles. But when you go down, you look at it from this perspective right over here, it's also 90 degree. It's also 90-degree bond angles. Wow, this is pretty cool, right? This is pretty cool. So yeah, this is octahedral. You have 2 going away from you, so you have 2 parts sort of going away from you. So if you kind of look at it from this perspective, 2 parts going away from you, 2 parts going towards you, 2 parts going towards you, and then you just have 1 in a sort of straight line. 1 in this sort of straight line. This is octahedral. If you remove 1, add a lone pair, square pyramidal is the name. Okay, it's going to be a squared pyramidal sort of structure. Okay, now what's going to happen is that octahedral, you can see that essentially all of the bond angles in octahedral are 90 degrees, right? So with the lone pair, of course, less than 90-degree bond angles. All right, what if we have 2 lone pairs? Square planar. All right, this is a square planar. The reason why it's called square planar is, well, if we ignore these lone pairs right over here and just look at it from the top, it kind of looks like some sort of square, right? It looks like some sort of square in a single plane, right? So this is square planar. And this square planar is going to have 90-degree bond angles. You can think about it as sort of, I guess you can think about it as, the repulsion from this electron and the repulsion from this electron right over here. They sort of cancel out their repulsion effects, right? The electrons up here and the electrons down there, they kind of cancel their like repulsion effects. So this is going to be like symmetrical, right? In terms of, repulsion and everything. Now, if we take away another atom, now we have a T-shaped molecule. All right. So imagine if we just took one of the square sort of atoms in this sort of square planar structure and we just replaced it. Well, if we removed one of it, now it's going to just look like a T-shape, right? So there we go. That is going to be the T-shaped structure. T-shaped structure, of course, less than 90 degrees because you have the electron. You have one of the electrons now. Now it's in the same plane. Now it's going to be in the same plane, right? You have one of the electrons, now it's going to be in the same plane as sort of the other 3 atoms. So that's when the repulsion is felt, okay? If you're ever dealing with something like symmetrical like this, right, where sort of the repulsion effects cancel out, or even in this linear structure, right, you can see sort of these 2 electrons, they're kind of going this way, and then this electron is repelling sort of this way, right? So if their repulsion effects sort of cancel out, well then, the shape isn't really going to change, right? Notice how you have these electrons right over here. They're in sort of this plane right over here. The other electrons are in the triangle plane here. So, that's another way, you can kind of visualize that. Anyways, T-shape less than 90 degrees. And finally, well, last but not least, linear structure. All these 4 electrons right over here, all these 4 lone pairs right over here, their repulsion effects also sort of cancel out each other. And ultimately, the bond angle between these 2 atoms is just going to be 180 degrees. All right. And there we go. All right. Just to show you guys. Boom. Linear. All right. Wow. Those look like, I don't know why. Those look like, those sort of like balloons you see at like a carnival. Like the clown like wraps up like a balloon. And it's like, they make it into like a shape. Anyways. Like this. Yeah, this is going to be the full Vsepr theory. And the thing is that there are actually more structures than this. I mean, it's only like, I'm pretty sure it's only like a couple more. Like, there's like some atoms, sorry, some molecules with a steric number of 7. And one example of this, uh, what's an example of one of steric number of 7? Hmm. Well, let's see. Let's think about iodine heptafluoride. All right, so you have one iodine in the middle, and remember iodine, whatever. This is going to have 7 valence electrons because it's a halogen, and you're going to have 4 fluorines surrounding it. 5, 6, 7. Right? Remember that fluorine only needs to bond once, right? Only needs to bond once in order to gain its full valence shell. And this is when you're dealing with atoms that are bonded to hella other atoms. Well, sometimes the octet rule actually has to be broken, right? Because I mean, there's not really another choice, right? If you're a central atom, you're trying to bond to all these other atoms, you kind of have to break the octet rule. Like, there's not really, you can't really escape that, if you know what I mean. So that's going to be like one. This is going to be sort of like one exception to, like, the octet rule, when you just have like way too many atoms that are bonded to you, right? And I am almost done drawing out my structure, so I am going to 3, 4, 5. All right, done. All right, let's get bonding. Okay, so that's going to create a bond. 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 That is going to create a bond. Boom. And boom. All right. Now you might be wondering, how is this going to look like in 3 dimensions? And my answer to that is that, well, I mean, the maximum that this will get to is an octahedral, so 6 steric number. But I like to imagine it like this. So trigonal bipyramidal, right? You guys know that for a trigonal bipyramidal structure, this is going to look like this, right? Where you have sort of these 2 atoms on the edge, right? And then if you were to zoom up and look at it from a top view, this is going to be a sort of triangle, right? Imagine this shape right over here, except it's a pentagon. So imagine trigonal bipyramidal structure, except that you add 2 extra atoms to this plane. So there's like 1 atom here and then 1 atom here, right? So it's like a pentagon shape. That's what iodine heptafluoride would look like. All right, and this structure is actually called, I'm pretty sure it's called pentagonal bipyramidal, and you can kind of see why, right? You sort of keep the bipyramidal, but instead of trigonal, you add pentagonal, right? There's actually, I'm pretty sure, there's actually like a theoretical sort of molecule that could be created or something like that, and it has like a steric number of 8. The one with a steric number of 8, pretty sure it's called like square antiprismatic, something like that. I don't know, actually. Y'all gonna have to search that up, but yeah. From steric number 2 to 6, that's pretty much all you need to know. Now let me start to give you some like common sort of atoms. I'm sorry, I don't know why I keep saying atoms. Now let me give y'all guys like specific molecules to help you guys remember this. All right, so you can remember that one thing that has a linear structure is CO2. All right, CO2 has a linear structure. You can just draw out the Lewis dot diagram like this, right? This is going to have a linear structure, even though it has double bonds, right? It's going to have the same pretty much structure. Yeah, you can also like sort of play around with this, right? See that CO2, this is going to be a linear structure. For a trigonal planar structure, well, one thing you can associate that with, beryllium, let's see, beryllium trifluoride, BF3. All right, that's also going to have a trigonal planar structure. All right. I mean, this simulation gives you sort of examples of, I'm pretty sure all the structures actually. Bent shape. This is pretty light because you can just think about not H2O. That's the other bend. You can just think about sort of what is it? Shoot, bro, guys, I'm having like a little brain fart here. Sorry, guys. SO2. Yes. Sulfur dioxide. There we go. Sulfur dioxide. All right. Sulfur. It's going to be like this. Sorry. Right? It's going to have 1, 2, 1, 2 to the oxygens, and then it's going to have 2 lone pairs remaining. And yeah, that's because a sulfur has 6 valence electrons originally. So if it allocates 4 of them for bonds, right, then that's going to lead you to 8 electrons plus the remaining 2, that's going to be 10 electrons, right? So that's going to be SO2. Tetrahedral, that's just CH4. You just think about CH4 for tetrahedral. Yeah, it should be there. Yeah, CH4 tetrahedral. For trigonal pyramidal, I just like to think about ammonia. This is how I remembered it. Ammonia, right? Ammonia looks like this, right? You have NH3, right? And then you can have sort of the lone pairs up top like this, right? If you want to draw like a simple Lewis top diagram. There's ammonia for that, and bent H2O, water. There's a reason why it's polar. There's a reason why it's bent. All right, trigonal bipyramidal, this is where things get a little bit like funky. So I'm pretty sure there was like a phosphorus one. Pretty sure it was like phosphorus pentachloride. Phosphorus pentachloride, PCl5. That is one example of a trigonal bipyramidal. Now let's see, for a seesaw, for a seesaw one, it's just going to be SF4, sulfur tetrafluoride, sulfur tetrafluoride. All right. And yeah, because like sulfur, remember SO2, right? It has 4 bonds here, and it's going to have a lone pair here. Look at sulfur now. Sulfur now has, instead of a double bond, imagine if these double bonds were single bonds, except sulfur had like 2 other atoms to bond with. So it still bonds 4 times, right? SF4, right? All single bonds now instead of double bond, and still going to keep this lone pair up top. But because now it has 5 electron regions, right, then the structure is going to change. For T-shaped one, chlorine, I'm pretty sure it's chlorine, and then trifluoride, right? Chlorine trifluoride, that's going to have, 2 lone pairs, right? Yeah, it's going to have 2 lone pairs because chlorine has 7 valence electrons in total. If you bond it to 3 atoms, then it's only going to have 4 valence electrons remaining, aka 2 lone pairs, right? So yeah, there we go. And then for linear, this is xenon difluoride. All right, in fact, noble gases can bond sometimes. Noble gases can bond sometimes. And then for octahedral, that's going to be sulfur hexafluoride. For square pyramidal, bromine pentafluoride. For square planar, that's going to be xenon once again, and then this is going to be tetrafluoride. For a T-shape with a steric number of 6 and linear with a steric number of 6, these are mostly like theoretical, like sort of like in the real world, like you probably would not find this. So yeah, that's pretty much it. Have a good day.